Gold can be made artificially, but in this video let's find out how the pure gold processes and find the answer to how gold is made. Let's start with today's gold video. Gold's color is owing to its electrical structure, which absorbs electromagnetic radiation with wavelengths shorter than 5600 angstroms, yet reflects yellow light. Gold's chemical stability is based on the instability of its compounds it forms with water and oxygen. This permits gold to be refined from less noble metals by oxidizing them and separating them as dross from molten gold. Gold dissolves easily in hydrochloric acid and sodium cyanide. Gold dissolves easily because it forms stable complex ions. At 1064 degrees Celsius, gold melts. Its high density allows placer mining and gravity concentration. The face-centered cubic crystal structure allows it to be molded into complicated shapes without specialized metalworking equipment. This led to its early use in jewelry and ornamental products. Exogenetic and endogenetic ores are gold's principal sources formed within the earth. Alluvial gold is a popular exogenous ore. Riverbeds, streambeds, and floodplains contain alluvial gold, always tiny gold particles. Weathering by wind, rain, and temperature creates alluvial gold deposits, most mined in antiquity. Exogenetic gold may also occur as oxidized ore bodies created by secondary enrichment, in which other metallic elements and sulfides are leached away, leaving gold and insoluble oxide materials. Endogenetic gold ores include vein and lode occurrences of elemental gold in quartzite or quartzite with iron sulfide materials, mainly pyrite and pyrrhotite, Fe1xs. Alluvial gold concentration is unsuccessful in sulfide ore deposits because gold is so finely scattered. 80% of Earth's gold is native. The largest 12mm nugget weighed 92 kilograms. Native gold contains 0.1 to 4% silver, 20 to 45% silver-gold alloy. Light yellow to silver-white, it's found in silver sulfide deposits. Tellurium gold minerals, calaverite, and sylvanite. Rare gold is economically worthless. South Africa, Russia, Canada, Australia, Brazil, and the US have the most gold ore deposits. South Africa's largest gold deposit is Witwatersrand. Mining and concentrating. Ore deposit affects mining and processing. Low-grade oxide ore isn't cost-effective to treat. Explosives crush them for cyanidation extraction. 100 meters long, 15 to 30 meter tall heaps are possible. High-pressure hydraulic hoses sluice bank and floodplain sediments. Alluvial deposits require little or no communion. They are concentrated using gravity methods such as jiggling or tabling, which capture larger gold particles while allowing sand and gravel to flow through. Endogenetic deposits typically include gold in a base metal sulfide. These deposits are mined, crushed, and treated before gravity separation and froth flotation. Extraction and refining. Amalgamation. Amalgam is formed when tiny bits of gold or silver are exposed to liquid mercury. Gold and silver are concentrated through this process. A slurry of ore is passed over mercury-coated copper plates. The ore and mercury are mixed in a cylindrical or conical vessel called an amalgam barrel, or the ore is ground in a ball mill, rod mill, or pebble mill to liberate the gold from the mineral matrix, and then mercury is added to the mill and the grinding is continued until the gold dissolves in the mercury. Mill discharge is when the denser amalgam is discarded. The amalgam is filtered and washed to eliminate any remaining contaminants before the mercury is removed. Because of concerns about mercury pollution, the use of amalgamation has been restricted. Cyanidation. Gold is usually recovered via cyanidation. Cyanidation oxidizes and dissolves gold in alkaline cyanide. In the Elsner reaction, atmospheric oxygen dissolves gold in sodium cyanide to generate sodium cyanorite and sodium hydroxide. Once dissolved, the gold solution may be extracted. Vat leaching is used for cyanidation when processing ores with a greater gold concentration. It involves keeping a slurry of ore and solvent in large tanks with agitators for several hours. Heap leaching is used to extract gold from uneconomical sulfide ores. Massive ore mounds are sprayed with sodium cyanide, which dissolves gold. Due to low gold concentration, the vat leaching circuit uses large amounts of solution and solids. Bypassing expensive solids-liquid separation equipment, initial expenditure was reduced. Activated carbon may be added to the ore slurry before or after gold solubilization. Passing the slurry over a screen separates granular carbon from the ore. The gold is subsequently recovered from the solution using electrowinning on steel wool or the Merrill-Crowe technique. In the second procedure, oxygen is removed from a gold solution, filtered via a press, and then reduced with zinc metal. Extraction from refractory ores. Many gold ores and concentrates are unsuitable for cyanidation because of impediments such as compounds that eat the cyanide reagent before it can dissolve the gold, preferentially absorb the gold as it dissolves, and entirely enclose the gold particles, rendering them inaccessible to the cyanide leach solution. Pyrite, pyrrhotite, and arsenopyrite are all examples of refractory ores. Gold may be extracted from these substances by oxidizing them. In order to remove sulfides, most gold-bearing materials are roasted at temperatures between 450 and 750 degrees Celsius. It is possible to oxidize minerals in an aqueous slurry by subjecting it to high heat, pressure, and oxygen-containing gases in a high-pressure autoclave. Following oxidation, gold is recovered using cyanidation. Refractory ore plants need skilled builders and managers. Refining. Zinc, copper, silver, and iron are found in amalgamated or cyanided gold. Miller and Wohlwill are two purifying procedures. The Miller method uses the fact that gold impurities mix with gaseous chlorine more easily than gold at temperatures above its melting point. The impure gold is melted and then chlorinated. Impurities produce chloride compounds on molten gold surface. The Miller procedure is fast and easy, yet it generates 99.5% pure gold. Electrolysis boosts Wohlwill's purity to 99.99%. In this method, impure gold is immersed in hydrochloric acid and gold chloride. The casting acts as an anode when exposed to an electric current. The anode dissolves, and contaminants flow into the solution or settle as insoluble slime. The electric field causes the gold to migrate to the cathode, where it is purified. The Wohlwill method generates high-purity gold, however it needs a pricey inventory of gold for the electrolyte. Direct chemical purification and recovery as elemental gold speeds gold production and practically eliminates in-process inventory. Refining from scrap. Processing gold scrap depends on its gold concentration and extractability. The majority of the gold may be recovered by cyanidation or aqueous chlorination, and the residue can be smelted to recover the rest. Unless easily recovered by leaching, scrap containing less than 0.1% gold is recycled for pyrometallurgy. On-site melting of jewelry and scrap gold is common. Assaying. Fire assay is the most accurate way to determine gold, silver, and platinum group metals, excluding osmium and ruthenium, in ores or concentrates. This procedure includes melting a gold-bearing sample in a clay crucible with fluxes, lead oxide, or a reducing agent, frequently flour. Fluxes decrease the melting point of oxidic materials, enabling them to fuse, while flour reduces molten litharge to very small lead droplets. Lead droplets dissolve gold, silver, and platinum group metals, then agglomerate and descend through the sample to produce a metallic layer in the crucible. After cooling, the lead button is removed from the slag layer and heated to oxidize and remove the lead. The precious metals are in the dazzling bead. The silver is dissolved with nitric acid, and the gold residue is weighed. Platinum metals will change the look of the bead, and their concentration may be detected using an arc spectrograph. In jewelry, carat specifies gold content. Pure gold is 24 carats. Each carat is 4.167% gold, therefore 18 carats is 75% gold. Fineness refers to parts per thousand of gold in an alloy. 39% fine gold is 99.9% pure. The metal and its alloys. Pure gold has few practical uses outside as a currency. Many regards a country's financial stability in connection to its gold reserves. However, no government guarantees its currency's gold value. Jewelry is gold's most popular usage. Because it's soft, the metal must be alloyed to gain hardness and strength. Most jewelry alloys are gold-silver, gold-copper, and gold-silver-copper. Gold jewelry is usually 14 to 18 carats. Gold crowns and bridges are also prevalent. Platinum and palladium are often added to silver and copper for strengthening. Gold's high electrical conductivity and corrosion resistance make it suitable for plating electronic contacts and transistor bases and creating durable silicon solders. Gold's chemical stability makes it a poor catalyst. Occasionally, it's used as a substrate for platinum catalysts in nitric acid production. We hope you enjoyed the process of gold. Stay connected for more videos. Make sure you are subscribed to the channel along with turning on notifications.